Tonight we're going to be talking about solving systems of equations algebraically using substitution. This is a different method to finding the solution to a system of equations. Prior to this, we've been talking about graphing, and we know that where two equations intersect graphically, that is the solution. But sometimes we found that graphing just doesn't seem to make sense. So in this example, example 1, pause the video if you need to in order to write this down. We see that we've got two equations, y is equal to 3x and x plus 2y is equal to negative 21, and these two equations make one system. Alright, and it doesn't really seem to make sense, or it could be laborsome to try to solve the second equation for y, so that we have it in slope-intercept form. So there's a different way that we can go ahead and solve these, and this is using the substitution method. And basically, what I see here is that y is equal to 3x. And if I know that y is equal to something, in this case 3x, then I know that y down here is also equal to 3x. So in this example, what I can do is I can take and I can replace whatever y is equal to for what it is worth. So in this case, y is equal to 3x. So I know that I can say, instead of having 2 times y here, I could have 2 times 3x. So I'm going to rewrite this second equation. I'm going to have x plus 2. So instead of y, I'm taking it, I'm replacing it with 3x. 3x is equal to negative 21. Now this is really valuable because if I look at the equation I just wrote, I only have one variable in this equation. It's the x variable. So now I've got one equation with one variable. I can go ahead and combine like terms here and distribute. So I have x plus 6x is equal to negative 21. And this would be 7x then equals negative 21. Divide both sides by 7. And x is equal to negative 3. Now what we've done here is we've found the x coordinate in the ordered pair that is the solution to this system. So I found that x is equal to negative 3, but now I want to go back in and say I need to have that second part of the equation, so, or the second part of the ordered pair. So where I already have found, I've already found in this ordered pair that's my solution, the x value is negative 3, I then have to come back in and say, oh, what's the y value? And the way I do that is I substitute now, if I know that x is equal to negative 3, into one of my original equations. It looks like the first equation is going to be the easiest to do that with. What is y equal to? Well, if x is equal to negative 3, then y is equal to 3 times negative 3, where I've just taken out the x in that original equation and put in a negative 3. So I think that y should then be equal to negative 9. And I'm going to go ahead and check this. I'm just going to check this. And the way that I do that, I'm going to change to a green pen here. The way that I check that is I need to then determine whether or not for each equation, can I substitute in negative 3 for x and negative 9 for y and it be a true statement still. So for this first one, I'm going to start, instead of saying y is equal to 3 times x, I'm going to take out those variables and put in what I think they're worth. So I've got negative 9, I think should be equal to 3 times negative 3. And here I've got 9 is equal to negative 9. Or negative 9 is equal to negative 9. That one works. So I'm going to take and do it. I have to do it again to the second equation because we know graphically this is an ordered pair that should satisfy both equations, the first and the second one. So where I have x plus 2y is equal to negative 21, I'm going to take out the x. I'm going to substitute in what it's worth here, what I think it's worth, negative 3 plus 2 times negative 9. This should be equal to, I'm putting a question mark above it, negative 21. So this is negative 3 plus, this is going to be negative 18. And I think that's equal to negative 21. And I do find that negative 21 equals negative 21. When this is the case, it works in both equations, the first one and the second one. Then my solution here, or the point at which the two lines intersect graphically, is going to be, I'll write it here, negative 3 comma negative 9. And that's the solution to this set of linear equations. But let's talk about what this would look like in a story problem. So example 2 says, Mr. J challenged Mr. McDermott to see who could run the most miles in 2012. Mr. J had already run 20 miles before the holiday break and then ran 2 additional miles each day. I'm going to go ahead and highlight this. You don't need to write this out in your notebook, but what you should do is be taking down the information that's pertinent here. So this gives me the first equation. I'm going to highlight that in yellow. The second equation probably comes next then. Let's keep reading. Mr. McDermott had not run any miles yet, but he ran 4 miles each day during the break. So this is going to be the second equation. Alright, just keeping with the trend that we've been using here, we're going to go ahead and use the x and the y variables, and let's go ahead and start by defining our variables here. So x, let me make this a little bit. So the x is going to be our independent variable, and that's going to be, what's it say here? Mr. J had already run 20 miles each day. So this is going to be the number of days. And the y variable is going to be their total miles, they run. Okay, so we've defined our variables here, and now we need to write an equation for Mr. J and one for Mr. McDermott. Let's go ahead and do Mr. J in black here. So if Mr. J started with 20 miles and then he's running 2 additional miles each day, you're probably predicting in your mind what that is. It's going to be y is equal to 2x plus 20. And then Mr. McDermott, let's do him in blue. He hadn't run any miles yet, so his constant is 0, and he runs 4 miles each day during break. So he's running, his total is going to be 4x plus 0, but I'm just going to go ahead and I'm going to get rid of that plus 0, just to make this an easier equation for us. So here I have the two equations. Mr. J says y is equal to 2x plus 20, Mr. McDermott says y is equal to 4x. Now, if, like we did before, if I know that y is equal to 2x plus 20 here, then I know that in the second equation, whatever is up here can be substituted for the y value down below. So if this is what, if y is equal to 2x plus 20, I'm just going to take that y out and I'm going to put what it's equal to. So I'm going to rewrite this equation so that I have, change my weight here, so I have 2x plus 20, that's what y is equal to, is equal to 4x. So I've taken out the y, I put what y is equal to, and now I can solve. If I look and I've done this right, you'll see that I have one variable in this equation, just the x variables now. I'm going to start by subtracting 2x from both sides. First best step keeps my coefficient positive, and divide both sides by 2. And I know that x then is equal to 10. So x is equal to 10. What that means, if I think about, what did we say x was equal to? X was equal to the number of days. So it would take them 10 days. So it's going to be the x coordinate here. Let me just start by doing that down here. This means it'll take them 10 days to run how many miles? So let's go ahead, and if I know the x coordinate, now I need to go back into one of the original equations. That's one of these equations. It's one of these equations here, this one, or this one, to find the y value. And which one does it look easier to find the y value? This one. So if I know that x is now equal to 10, I'm going to say, well, y is equal to 4 times 10, and so y is equal to 40. Now let me interpret what this ordered pair means. So we found that our solution here is 10, 40. And if I said that x is equal to the number of days, so after 10 days, y is equal to the total miles, they will both have run 40 miles. And that's where they have run the same amount of miles each day. Let's keep thinking about Mr. McDermott and Mr. J in example 3. Example 3 says, one day, Mr. J and Mr. McDermott had a race. Since Mr. J had already run more miles, he let Mr. McDermott start 1 mile ahead of him on the course. During the race, both teachers ran at a rate of 6 miles per hour. How long would they have to run before Mr. J catches up to Mr. McDermott? Well, let's think about what's happening here. Again, let's start with our defining our variables. I'm going to do it right down here, if I can find where my cursor is. Grab a pen instead of a pencil. So x, let's say our x is going to be equal to, what do we have here? Both teachers run a rate of 6 miles per hour. So the x is going to be the number of hours, and our y value is going to be the total miles again. Alright, so let's say Mr. J is here, and Mr. McDermott. Because McDermott's such a long name, I was going to call Mr. McD. So Mr. McDermott got to start 1 mile ahead of Mr. J on the course. But it says they're both running at 6 miles per hour. So they're both running relatively slow. This is a y is equal to 6x. So Mr. J is running 1 mile behind Mr. McDermott, so he's going to be right here. Mr. McDermott is y is equal to 6x plus 1. And if we want to use a substitution method, then to find the intersection of these two lines, I see that here I've got y is equal to 6x. So this is what y is equal to. And here I've got a y. So I'm just going to take the y out of the second equation here and put a 6x in instead. So here I've got 6x from Mr. J equals, and then 6x plus 1 from Mr. McDermott. Now if I go to try to solve this for x, and I look at again and I see that I have one variable, I just have the x variable here. I'm going to subtract 6x from both sides. And here I come down and 0 equals 1. Wait a second, we know that 0 doesn't actually equal 1. Well, what we see we've done here is we've actually eliminated the variable term. So in this case, this is a no solution. And if I remember back to graphing these systems of equations, a no solution means that they should be parallel lines. And again, that's supported up here in the equations where both have a coefficient or both have a slope of 6. And they have different y-intercepts. One has a y-intercept of 0, and one has a y-intercept of 1. So these are both parallel lines that never intersect, meaning that Mr. McDermott will win the race because he started ahead, and Mr. J will never catch up because they're running at the same rate. Since Mr. McDermott got to start ahead, he stayed ahead. And the last example, this one's tricky. The reason why this one's tricky is if I'm using the substitution method, I don't have a variable term solved in either one of these equations. The first equation is x minus 2y equals 2. The second equation is 3x minus 2y is equal to 10. And if I look at the examples that I've worked with previous to this one, I see here that I've got y's, these two equations are solved for y, and even in example 1, I see that first equation is y is equal to 3x, so it's been solved for y. Down here, neither one of these equations has been solved for y or x, so I need to choose which one to solve for x or for y. And I'm going to choose actually to solve this first equation for x. And the reason why I do that is because x has a coefficient of 1 here. And because it has a coefficient of 1, I'm only going to need to isolate it in one step. Let me show you what that looks like. So I'm going to use my red pen. And I'm going to bring this guy down here. Like this. And if I have x minus 2y is equal to 2, all I have to do to get x isolated is add 2y to both sides. And once I do that, I now have x is equal to 2 plus 2y. So I know that whenever I have an x variable, and in this case, when I have an x variable in the second equation, the x variable is actually equal to 2 plus 2y. So here I see I have an x variable, and I know that that's actually equal to 2 plus 2y. So I'm going to go ahead and substitute whatever x is equal to. Where's my cursor? into that second equation. So here, let me show you. I have 3, but instead of x, now I've got 2 plus 2y minus 2y equals 10. Looks nasty, but in a second it'll be okay. I'm going to go ahead and distribute that 3. So it'll be 6 plus 6y minus 2y equals to 10. And a quick mental check I do is I see that now I have one equation with only one variable, in this case the y variable. But that indicates to me that thus far I've probably done the right thing. So now I can combine my like terms. It's a two-step equation. Divide both sides by 4. Y should be equal to 1. So here I think y will be equal to 1. And I'm going to go ahead and, oh goodness. Alright, I'm going to go ahead and think of my solution. I think my y variable in my solution is 1. I don't know what x is yet. But if I know that y is equal, if I think y is equal to 1, I'm going to go ahead and substitute y or 1 back in for y into one of the original equations, and I'm going to do it right here. So you'll see me then I have to find that x variable by saying x minus 2. Instead of y, I'm going to put in 1. So x minus 2 equals 2. Add 2 on both sides. And I think the x should be equal to 4. So here I'm thinking that these two lines intersect at the point 4, 1. And I want to just check and make sure, and I'm going to do that with a green pen. And the way, again, I do that is by saying, really quickly, I think my x value will be 4. I think my y value will be 1. And that should be equal to 2. 4 minus 2, well, we know that equals 2, so that's good. And I'm just going to do it for both equations. Again, this solution should work on both of the equations. If it doesn't, then it's not an actual solution to the system. So I have 3x minus 2y equals 10. Take out the x and put in a 4. Take out a y and put in a 1. I think that should be equal to 10. So this is going to be 12 minus 2. Oh yeah, that equals 10. So 10 equals 10. And when I've confirmed that it works for both of those equations, then I know that this point, this 4, 1, is a solution to the systems. There you go. Make sure you get those in your notes, and I'll see you guys tomorrow.